Thank you, everybody, for joining the webinar, Achieving Speed and Precision, Reliable Activation of Nicotinic Acetylcholine Receptor alpha-7. The acetylcholine receptors are ionotropic ion channel receptors that play a key role in cholinergic signaling in the central nervous system. And the alpha-7 subunit, which is one of several subtypes of the acetylcholine receptors, is the most abundantly expressed subtype in the central nervous system, as well as the peripheral nervous system. And it's also expressed in other tissues, immune cells, etc. But there's been numerous studies that have indicated that it's a promising target for a number of disease states that include everything from neurodegeneration to inflammation, chronic pain, and more. And there's now molecules progressing through the clinic. One of the challenges, however, is subtype selectivity, and there's a number of challenges for developing assays to measure the activity of this channel and develop modulators. So this slide highlights some of the challenges surrounding the development of an assay for reliably measuring the activity of this channel to develop modulators or that could be used as potential drugs. And lots of different things, the temperature sensitivity, the calcium permeability, receptor modulation, uh, your selection of what kind of agonist you want to use. These are all challenges that need to be addressed when you're developing an assay. But today we're going to focus on two of these challenges in particular. In the first case, we're going to focus on the development of robust expression platforms for the channel. And for this, today we're going to have Dr. James Costanton, who is the Scientific Market Development Manager for ion channels at Eurofins/DiscoverX. And the second aspect that we'll cover in today's webinar is how to deal with the property of the channel, which is this very fast desensitization. And for that, today we have Dr. Ilka Rinke-Weiss, who is a senior scientist at nAChR working out of our headquarters in Munich, Germany. To go a little bit deeper into the challenges of the fast desensitization, I think it's useful to talk a little bit about the development of our recording device. So today's webinar will focus entirely on our high throughput automated patch clamp system called the SyncroPatch 384. Now, this system has been developed to do drug screening. It can also do biophysics, across a wide variety of assays, anything from the academic lab all the way up to pharmaceutical companies who need to do drug screening. And one essential component of this machine is what we call the patch clamp chip. This is the site at which the cells are patched. At nanion, we use entirely borosilicate glass substrate. And over here, you can see the concept of the planar patch. We have a micron-sized aperture in each well where the cell is patched, and you can form whole cell configuration. I think most people who might be joining this webinar are familiar with this concept. Much like we've worked over the years to improve the overall performance of our systems in terms of the liquid handling, the drug compound dilutions, our patch clamp module, we're also working to improve the properties and performance of the patch clamp chip itself. Second generation chips were developed several years ago, which broadly improved performance across all types of assays. And this says consumables can drive applications, but I think oftentimes it's the reverse. People were very interested in working in systems where we don't have fluoride ions in the solutions, and which is a commonly used thing across all companies who are developing patch clamp systems at high throughput. And so our third generation of chips were designed specifically for operating under fluoride-free conditions. Now, along come people who want to do mechanically gated channels. And this is our fourth generation of patch clamp chips, which have very precisely positioned holes so that we can use shear stress to activate by a solution flow across a cell, channels like piezo-1. It also turns out that this fourth generation of chip is what will be the topic of Ilka's part of the webinar, as it can also be applied to ligand-gated ion channels. And finally, just to mention that we have a very new product, which is our fifth generation of chips with smaller aperture sizes. And these are specifically designed for recording from organelles such as lysosomes or very small cell types. Our second generation chips give you broadly robust success rates for recording across all cell types, anything from an HEK cell to a induced pluripotent stem cell derived neuron or cardiomyocyte, all the way up to primary cells such as red blood cells or T cells. Over here in the upper right, example of a fifth generation chip recording from a lysosome and measuring the activity of TPC2. And in the lower left, now mechanoactivation of piezo-1 via shear stress using our fourth generation of chips with the precision positioned holes and as another application of these precision position holes, a fast ligand gated ion channel trace here from a nicotinic acetylcholine receptor. And with that, I think we can proceed to our first presenter, Dr. James Costanton.
Okay, Tim, thanks. I'll go ahead and start sharing and get my video on here in a second. As Tim mentioned, I work at Eurofins DiscoverX, so we're the products company of Eurofins, and I've been here about 3 years or so. Prior to that, I was at nAChR, and I've been in the automated eFIS business for the last 22 years or so, something like that. Okay, so most people aren't all that, or most ion channel people, I should say, aren't all that familiar with DiscoverX. So we are located in Fremont, California. I'll give you all of our target assays here in a moment. But I joined almost 3 years ago to manage the ion channel product portfolio. So today what we're going to do is I'll show you some data from the validation of the nicotinic alpha-7 channel with the 3 subunit as well. And I'll show you data from the stable cell line and also for a new product that we have, ready-to-assay frozen cells. So DiscoverX was founded in 2000 and became the products business of Eurofins Discovery in 2017. We have over 1,000 functional assays available for popular target classes and including the 3 big target classes, GPCRs, kinases, and when I joined managing the ion channel products. We are based in Fremont, California, which is also where I live. We just moved into this building 2 weeks ago, so it's been a scramble to get everything together, but we're moved in. I have my slides. We're all set here, so we're good to go. So our ion channel lines, I have a long history with these. They're suitable for discovery, screening, lead optimization, and also safety. They're trademarked as precision lines. And we also, as I mentioned, we're coming out with ready-to-assay frozen cells, also trademarked with precision. We also have trafficking assays for ion channels, and we also have custom development capabilities. So if you want a custom cell line made, we can do that. So some of the history, a lot of people don't realize where our cell lines came from. I do. So they came from Cytomics. They started off at Cytomics in the UK, Cambridge, back in the early 2000s, and I actually was working with Cytomics at the time on a hERG channel with them. And so Cytomics began the collection back in the early 2000s. They were acquired by Serologicals, who were then acquired by Millipore, and then they were changed to Merck Millipore. And then Eurofins acquired Merck Millipore. So then that they became the owners of the cell lines. And then when DiscoverX was acquired in 2017, we became the products division. And so now we manage all the products for Eurofins out of Fremont, California, including the precision ion channel cell lines. Okay, so these are the actual, this is our portfolio of cells, of ion channels, I should say. I'm not going to go through these individually, obviously. We have a few more coming online soon, another GABA and a TRP M8. So as I mentioned, I'm not going to go through any detail, but we have a very large collection of quite good cell lines. So it's kind of funny, when I first started, it just happened to turn out that the very first target that we needed to validate was the alpha-7 cell line. And I was kind of complaining to my colleagues that, this is one of the toughest cell lines to work on. Can we start with something simple, like a K channel or a sodium channel or something like that? And the answer was no. But basically, we needed to validate these in a hurry. So I actually ran them. I always like to run in single hole mode. Those of you that know my history, I was involved in the original population patch clamp project, but I always like to run things first in single hole mode. So we ran the cell line in single hole mode, and I wasn't expecting to see much of a current, but I was actually quite surprised to see the current's very good expression. So this is actually the very first run that we did. Seals were quite good in single hole mode. The expression was good, but not huge currents, but they were there. Not surprising because these channels desensitize very rapidly before they really fully activate. So they're notoriously hard to work on. So anyway, I was just happy to get a signal at that point. Um, so as I'm showing, we had a robust expression of the rapidly desensitizing currents. Then I actually was we in researching how to validate them, and without really having to try to do the pharmacology on the acetylcholine current itself, I realized the previous work had been done with these positive allosteric modulators, and so the data here that I'm showing is actually from a data sheet that this data is from the Patch Express, which you may know in the early days, the early 2000s, was a single hole platform. Um, and then also the reference here is from Raymond Hurst, who published a paper on these PAMs back in 2005. So I was quite pleased to see that these currents get enormous with this PAM. So it made my life a lot easier in terms of showing that the currents were that the channels were expressing. So what I did here was we looked at we put acetylcholine across the entire plate. So we had the very spiky currents here on the left half of the plate, and on the right half of the plate we added the PAM PNU, and we got extremely robust currents out of it. And then we wanted to do a blockade of them with a specific blocker of the nicotinic acetylcholine current, which we did next. So this is a summary of the PNU PAM data. So you can see a very robust increase in the currents on the right half of the plate versus the left half of the plate and the previous data that I just showed you. So very nice uh, improvement or increase in the cell currents with the PAM. Okay, so then I actually had not worked a lot with ligand-gated channels, so we got a little creative here. And what we did is we added acetylcholine and the PAM across the entire plate. So we're activating everything all at once. But at the same time, this is what I would call a single shot experiment. We were adding the blocker at the same time, so at the highest concentrations. So we're essentially blocking the channel and also trying to activate it at the same time. So as you can see, we got a reasonably good dose response curve here with no currents here on the left of the plate, and then larger currents as we go to the right, decreasing the concentration of the blocker MLA. And at this point, we had switched to 8-hole population patch clamp plates just to get a smoother signal across the plate, just to average out the signal. So this is the dose response curve for the previous experiment that I just showed you. As you can see, full block at 330 nanomolar MLA, and then we got a fairly decent fit of the dose response curve, a little less than a nanomolar for the IC50 for the block by MLA. Okay, so as I mentioned, I just kind of winged it on the first experiment using the default settings on the SyncroPatch, and we got reasonably good currents, and then the PAMs increased the current quite a bit. But what we did then was we wanted to improve the parameters of the puffs of the ligand puff, which is the way these experiments are done, where the ligand is puffed out to the cell and then pulled back quickly. And so we got some advice from Nana on how to improve that. I should also mention that we're switching gears now to the the Ready-to-Assay version of this cell line. So it's the RTA cells is what we're working on. We actually in the experiments that I'm showing here, it's from the pilot lot of the cells of the RTA cells. So they actually contain 4 million cells each. We decided that our finished product should contain 6 million cells each per vial. And I mentioned that because I actually made a mistake. We made a mistake in the first experiment where we ran kind of light on the cells. Still got good results, but yeah. Anyway, so I ran the first experiment at 4 million per or 8 million per run rather than 12, and so you'll see the results there. With the suggestions from Nanaon, we got improved resolution of the nicotinic currents in the absence of the PAMs. And you can see that here. This is again repeating the experiment, this time in 8-hole plates as well, with 300 micromolar acetylcholine, with some of the technical aspects here on the left. As I mentioned, this run was a little too dilute, so the seals were compromised. I actually cheated a little bit and used a lower seal filter on this one, but you can see that the currents are there, although the seals are compromised because the cells were run a little bit too dilute. However, when we add the PNU, we get the very robust increase. And in fact, we saturated the amplifier in quite a few cases. So this was just kind of a quick and dirty experiment just to show that the RTA cells behaved in a similar manner to the stable cell line. So it obviously worked, that the PNU really increased the current to the point of saturating the amplifiers. We wanted to, so this is a summary graph of what we saw. And again, with the RTAs, I'll be showing RTAs from here on out, similar increase to what we got with the stable cell line. Okay, so we decided to try a different PAM. The first PAM, the PNU that we used, basically eliminated the desensitization of the channel. So you saw, let me go back. You saw that there was absolutely no desensitization out here at the longer time course. This other PAM we wanted to try was supposed to increase the magnitude of the currents, but also maintain some of the desensitization. So this was the first experiment we did with this. We had good success rates. We ran the cells at the right concentration. So this is 12 million cells per run. So that would be 2 vials of the product. We got a really nice potentiation of the currents, peak currents, and they also continue to desensitize. You can see a couple of clamp issues on here, but that's just because the currents are so huge. But really nice success rates here. Seal filter appropriate for an 8-hole plate. So we decided to, because of these decent results, we decided to move forward and go ahead and do a dose response curve with the activation of this NS-1738. So this is again the control conditions prior to the addition of the PAM. Again, good success rates. We ran the cells at the right concentration again. Success rates of about 83% with appropriate filters for an 8-hole plate. Again, we got the big increase in the peak currents. This is actually a much higher dose. This is the highest dose in the dose response curve, so 50 micromolar I'm showing here. Huge increase in the peaks. Desensitization still present for the most part. And then we went ahead and I'll show you the dose response curve here. So again, at the highest concentration, went from 50 micromolar all the way down to 0.05 micromolar. And you can see big potentiation across the higher concentrations. And then it gets much less, almost to the point of no potentiation here on the right. And these actually, I did this experiment actually right before the move to the new building. So this has been a kind of a hectic last couple of weeks here, but fun as well. So this is the summary of the results. I actually have been trying to plot this in Prism and not having much luck. So the bar graph tells the story quite nicely. This is basically the first sweep. So in the absence of any PAM, and then the huge increase that I showed on the previous slide with 50 micromolar PAM, and then decreasing the concentrations all the way down to where we have very little potentiation. And I believe that's my last data slide. And I just wanted to, at this point, just mention that this cell line is not a product yet, but we're in production with it right now because of the decent results that we got with the pilots. But I also wanted to show you a little bit about some of our other RTA format cells. So basically, we decided that we would convert, start with our cardiac safety panel, converting them into ready-to-assay cells. So we did the HERG, we did the CAV 1.2, and we did the NAV 1.5. Converted the stables to to RTAs. And then we started with the pain panel with NAV17 and NAV1.8, and we are working on more in the pain panel. But as I mentioned, the work that I showed here on the nicotinic channel was all from the pilot lot. So these are in production now, and we expect the results to be quite similar. So this should be a product within the next month or so, the nicotinics. And I just show some raw data from the herd, the CAV1.2, NAV15, and 17 and 18. And with that, I think I will hand it back or over to Ilka.
Perfect. So first of all, thank you, Tim, for giving us the insights into the validation of the alpha-7 nicotinic acetylcholine receptor cell line. And I also want to thank you, Eurofins, DiscoverX, for providing us this stable expressing cell line, because this made a lot of fun with further development on the assay, or the assay on the SyncroPatch 384. And as Tim was already providing in his introduction, that developing a patch clamp assay to study the alpha-7 nicotinic acetylcholine receptor presents several challenges. And these challenges are both biological and technical nature. And one of the most significantly hurdles is the rapid desensitization of the alpha-7 nicotinic acetylcholine receptor. They desensitized almost immediately after exposure to the agonist, and this makes it very difficult to obtain reliable and consistent recordings. So, and this leads often to poor reproducibility of the data. So, and you had already seen in the slides what Jim was presenting, that the current desensitization occurs within milliseconds, and this limits, of course, the time window for observing the receptor activation. And one of the typical mitigation strategy to use, one of the typical mitigation strategy for the fast desensitization is the usage of this positive allosteric modulators, what Jim was also presenting before, and such as the PNU or the NS compound. However, those modulators dramatically affect the receptor's response to the agonists, and it also changes or alters the receptor kinetics, and this of course complicates the analysis of the evoked currents. So we took on the challenge, and in the second half of this webinar, I want to highlight how we could optimize the location and the time of the agonist exposure. And I also want to show you which results we have achieved with this optimization strategies. So we developed the assay also on the SyncroPatch 384, which is the automated patch clamp device, which is based on the planar chip technology. This is provided in a 384 website format. The bottom of this chip is made of borosilicate glass, and the holes are made within this glass, and each well represents one of the patch clamp sites. And you can have one hole within one well or multiple holes. And you can see here exemplified well of the standard chip configuration with the borosilicate glass and the hole on the bottom of the chip, and the pipette tip, which is serving the external solution, and the cells, which is located on the right-hand side or right edge of the well. And the cells get attracted towards the aperture by applying pressure underneath of the chip. And the currents, which are mediated by the ion channels, they are measured over the electrode, and this is connected to a 384 probe amplifier, where the signals get then amplified and digitized, and which you can then record and analyze with the screening software. You can see here already in the standard chip configuration that the hole, which is presented here, is a little bit offset of the pipette tip outlet. So we had the idea to adjust the position of the hole more towards the pipette outlet. This would be shown here in this cartoon. And if you want to see a top view of the well, you can see that we match the patch hole more closer underneath of the pipette tip outlet for the single hole configuration and for the multi-hole configuration. And further, we combined this chip adjustments with the optimization in the liquid handling capabilities of the BioMac-I series. We designed a solution addition procedure for fast and brief compound application, which is so-called click and puff. And this we used to optimize the solution addition speed and volume. And here on the right-hand side, you can see the principle of this click and puff approach. In dark blue, you see the amount of liquid, which is aspirated from a labware and then applied with a certain dispense speed onto the hole within the well. And all the solution gets removed after a defined exposure time. And in the meantime, you record current while applying the solution. And here you can already see on the right-hand side that dispense speed in applying the ligand matters a lot on the current kinetics, and faster dispense speed enables much faster kinetics of ligand-gated ion channels such as the nicotinic acetylcholine receptors. So the effect of the adjustments which we have made and the optimizations I will present in the next slide. So here again, you see a graphical user interface of the screening and data analysis software used on the SyncroPatch 284. And the graph shows the raw data traces of the alpha-7 nicotinic acetylcholine receptor expressed in HEK cells. And they are recorded in this particular example on the adjusted chips, which are called FM-STIM and PC384. And we applied the ligands acetylcholine and nicotine in a dose response manner, and each well got a single concentration of it. And 3 control applications were applied before max dose of the ligand was applied. And then this experiment was performed on multi-hole chip, which is serving 4 holes within 1 well. The data which you can see in the 384 well plate format represents the color code for the C resistance. And in green, you can see all wells which have a C resistance more than 130 mega ohm. And when you multiply this by 4, because you have 4 holes, you have more than 500 mega ohm per well. And the C resistance is depicted here in this bar graph. This bar graph compares the C resistance between the standard chip in dark blue and the C resistance of the adjusted chip in turquoise. And you can see already for the single hole configuration that the C resistance is much more higher after cell-catch addition. And this is also the tendency for the multi-hole chips, as because the C resistance is one of the main important parameters to assess the quality of the data. And also among others, you can see here in this bar graph that based on the parameters, we validate the wells passing or failing the quality check mark. And in turquoise, again, the FM-STIM chips, and you can see that the number of successful wells is increased among the standard chip configuration, which means that you have more wells which are can later be analyzed and fulfill all criteria. Here's another bar graph demonstrating the C resistance over time at the experimental start. So at the very beginning of the recording of the currents, And at the experimental end, which is the last edition of or the last recording of the currents, and you can see it's very robust from start to end for both chip types, but you see a tendency for a bit more or higher C rates for the multi-hole chips for the FM-STIM configuration. In the next slide, I want to show you a comparison between the different chip types in current amplitudes. Here you see the single rod, the average rod traces of a single well configuration. On the left-hand side, the FM-STIM or adjusted hole positioning chips and the standard chip configuration. For the single hole chips, you might not see so many differences in the current amplitudes for different concentration of the acetylcholine, and also not so much in the first instance for the multi-hole chip with 4 holes. But if you can see here with the multi-hole chips presenting 8 patch holes within one well, you can see an increase of the current amplitude, and also you see different kinetics already. And this is also depicted or summarized in this bar graph here, presenting the average current amplitude compared between different chip types. And there is a tendency towards higher average current amplitudes for the adjusted chips for the 1-hole configuration and the 4x configuration, and a significantly higher average current amplitude for the 8-hole chip configuration. And here in the lower part, I wanted to highlight the current stability over multiple additions of acetylcholine. I applied the acetylcholine first 3 times with the same concentration of 100 micromolar acetylcholine, and at the end a max dose of 1 millimolar. And you can see that the currents are reproducible in both chip types for the standard and the adjusted chips. But we also wanted to see or had a closer look on the current kinetics, because here in this 8-hole chip configuration, you can already see a difference. Our software is capable to calculate or measure the tau, which is a parameter which you could get from a mono-exponential fit to the raw traces. And we compared this parameter, the tau, between the 2 different chip types again, and you see that for the multi-hole chips, it's again a significant difference towards faster tau for the adjusted chip. And we also wanted to see whether the decay time from the minimum has been changed. And indeed, this is also the case for the 8-hole chips, where the decay time is much faster in the adjusted hole position chips. And also the time to reach the peak current amplitude is quicker in terms of the adjusted chip configuration. Then we wanted to have a closer look onto the general concentration response results for evoked responses by acetylcholine. You can see in this graph, when you compare standard chips versus the FM-STIM chips, that the fit curves are pretty much overlaying. So that means that we maintain the compound concentration responses among the different chip types. Jim was already presenting the 2 types of positive allosteric modulators. We also wanted to see within the experiments how the performance of these modulators is on the adjusted hole positioning chips. And you can see again the screening software depicting the raw data trace for the application of the acetylcholine in a reproducible, in a repetitive manner. And then in the 4th edition, we applied the type 2 positive allosteric modulator, the PNU. And at the end, the last 5th edition is the max dose of the PNU. And you can nicely see how the current gets affected by the modulator, and that the desensitization is abolished by that. EC50 is pretty steep, but this is fitting to the findings in the literature, and just confirming that all is good and tips perform as they should. But I also want to highlight here that performance of the cell was really well. So you see here all the pictures in green, they highlight the C resistance parameter, and it's really stable. And yeah, this was really nice to see over all of the experiments I had done. And you can also see in the concentration response curve that we have analyzed 316 wells of one experiment, which is a great success. And on the last slide, I want to demonstrate also an inhibitor and commonly used, which was also done by Jim. And again, you see how nice the data are. So the arrow bars are pretty low. It's really nice fitting to the literature volume. And one of the main highlights here is also that the reproducibility of the currents evoked with ligand, with acetylcholine, is really high. So you see no rundown of the current, and you could gain highly reliable data. In summary, the results which I have shown you now show that the adjusted tips show initial higher C rates, and also the currents were much more bigger and showing faster kinetics in terms of multi-hole configuration. And one of the biggest highlights here in this study was that we were able to get reproducible currents over multiple ligand addition. And then in conclusion, these results highlighted the reliability and robustness and accuracy of the FM STIM chip system. And it supports that the setup is in combination with the fast addition capabilities is well suited for repeated measurements and kinetic studies, and also dose response analysis without compromising for any data integrity or due to desensitization or due to leak. Yes, and by this I transfer to Tim again.
Okay, thank you, Ilka. That was a great presentation, and thank you, Jim, for another great presentation. I've got a question for you, Ilka. One question is regarding comparing the kinetics between the standard chips and the M-STIM chips. Was the dispense speed the same for both chips?
Yes, this was. Yeah, it was 100 microliter per second.
Okay, and I was going to say, yeah, it better be, right?
Yeah.
Yeah. Another question that just came in, and this was actually one of the questions I have. Is there really a difference in terms of the reproducibility, the current amplitude staying the same over multiple puffs? Is that also something you see on the standard chips, or is that unique to the F/M's chips?
This is actually a good question. I think we do see that there is a slight difference. We do see slight rundown on the standard configuration, but we probably need to quantify. So I think this was not so much, so it was not significantly different. But I could imagine, so I think the combination between this cell line provided by Eurofins and also this adjustment made it very robust in both cases. So
Okay.
yeah.
Yeah, well, having a good cell line, I know, is, essential.
Yeah.
Otherwise, you're going to be struggling.
Yeah, I
Another
agree.
another question just came through, and this is a question that actually one of our colleagues sent me through the chat, and it has to do with the recording temperature. I think there's some reports that some of the positive allosteric modulators, when they're measured at physiological temperature, let's say 36, 37 degrees centigrade, that you don't see an enhancement of the modulator at that temperature. Can you tell us, what temperature you were recording these at, and comment on whether it might be worth exploring physiological temperatures?
Yeah, so the experiments which I had done were performed on room temperature, and we are capable to perform experiments at physiological temperatures or also other types of temperatures. And I remember that we did it in the past, and I was discussing with a colleague of me that we had shown that there are changes in the current amplitudes when you change the temperature. So there is the sensitivity to the temperature is critical. And yeah, this is a really nice outlook what we could have recorded on the SyncroPatch 384.
Okay.
I agree.
Yeah, and Tim, I've only ever done room temperature
Okay.
so far.
Cool. Okay. Well, it sounds like something for the next round of experiments, maybe. And I've got another question just came through, which is a good one. In the experiments where you're doing multiple ligand additions and showing that really nice stable baseline, the question is twofold. First is, how far apart are those individual applications in time? And did you use anything to break down the acetylcholine, such as adding the enzyme acetylcholine esterase in the well?
We had not. So we had not used an enzyme used. I remember that we did that before with other targets on also acetylcholine receptors provided from other companies. Also to overcome this problem with the reproducibility. I remember that. And the time between the different additions, it was I think I haven't really looked into it. It must be something like 2 minutes or so. Okay. I think there's always time to pick up the ligand again from the labware, and I had no washing steps in between. So yeah, this was nice to see that even the outwash by removing the solution out of the well was fine. So there was obviously no ligand residues within the well, or just tiny.
Interesting.
Without affecting.
Okay. We're getting a few questions coming in now. This is great. I guess we have a question for Jim. It's an expression question, and this one is asking about the RIC3 that's also co-expressed. And this person wants to know if you have any data on comparing the parameters of the alpha-7 channel over different levels of RIC3 expression. So I think in the first case, do you have like a no RIC3 and a plus RIC3 or anything like that?
Yeah, we do not. My understanding is RIC3 is a chaperone protein, and the only the only cell line that we have with alpha-7 is with the RIC3.
Okay, thanks, Jim. Okay, here's a question for Ilka. It says, great presentation. The kinetics, you're seeing a significant difference for the 8-hole chips, but not for the other ones. Do you have any thoughts on why that might be the case?
Yeah, when you see the configuration underneath of the tip outlet, you see that the holes are sorted in a kind of square, and I can imagine that the location of the tips relating to the tip outlet might be not as precise. So it's maybe some wells or some holes contribute to the current more than others, and on the single hole configuration this is not the case, of course, because on the 8 hole you sum up the current, and some of them might be slower than the others, and then the kinetics are slower or look slower.
Okay. I think that makes sense. Yeah. I think we have another question that goes back to related to the cell line. It's for Jim, and this one is: have you ever compared alpha-7 parameters with a nAChR chaperone expression? I've never heard of nAChR, and it's a great name. But are you guys developing alternatives to the RIC3, like other chaperones?
Yeah, not for the alpha-7. I've heard of the nAChR for, I think, for one of the other nicotinics. I can't remember which one, but yeah, the nAChR, I have heard of that. It is a chaperone. It's specific for the one that's super hard to express. We've looked into it, but we haven't done much with it yet.
Okay, thanks, Jim. I had a question for, I guess this pertains to both of you guys. Actually, one for Jim. You're puffing on at 40 to 50 microliters per second. Ilka, you were going up to 100, which I understand is pretty close to the maximum that you can get. Jim, have you considered going to a higher puff speeds?
Yes, we have, but the truth is we have, we're managing 60 something cell lines, so we don't really have a whole lot of liberty to do sort of experimentation.
Yeah.
It's really strictly kind of a validate, to get into product. So we don't really have a whole lot of experiments that we can do just for fun.
Sure.
But
Well,
that would be a good one.
that's why you have Ilka, I guess. And so the other half of that question is, when you go up to these really fast dispense speeds, do you have concern that the cells might be, actually blown off the hole, or do you apply any holding pressure on the cell to keep it in place, or do you have to mitigate such effects?
Actually, I was not facing that in this regard. So I was also impressed that this was happening. I could imagine that this also the improvement of the seal within the on the adjusted tips is much higher, and maybe this also leads to the fact that they remain more stable even with this high dispense speeds.
Yeah, it's amazing because I did a little bit of work with the piezos, and I was really worried about this going up to 110 microliters per second. I was putting on a mild holding pressure of -30, so maybe that's not even necessary. It's remarkable how robust these cells are, and to really, once they're patched, they're really stuck tight. I was fascinated by this effect on your seal resistance when you're using these special precision chips. How do you account for that? If the cell, when it's dispensed into the well, is it the fact that it lands directly on the hole instead of maybe rolling across the floor first? How do you envision that? Something like that?
I could imagine that this is the case, because when the tip outlet is a little bit offset of the hole, then it takes a little bit longer to attract it when they are applied from the tip to the hole. So there is a bit of distance, but it's not so much when they are sitting direct underneath of the tip outlet. And I think this is also what we observe, that the cell catch goes faster. So this increase in seal resistance you see faster than in the standard chip configuration. Yeah, and I also want to point out, this is the initial seal rate. So the initial seal rate, you see the differences there, but at the end, so with the start of the experiment, and I also showed that in the slide, that the sealing on both chip types is comparable. Yeah.
Okay. So your ultimate success rate is comparable in terms of the seal resistance being maintaining over time.
Yeah.
Okay. Otherwise, I'm going to say everybody's going to want these chips instead of the other ones.
Yeah.
Otherwise, great. Okay. I think we've gone through. I apologize if I missed any of the questions. Thank you, Ilka and Jim, for presenting. Thank you, everybody who attended. Thank you for all the great questions. I also wanted to mention that we have some events coming up that we'd like to invite you to. We have the Nanian Technologies Membrane Physiology Symposium, second annual rendition of this. This will be in Napa, California, April 30th to May 1st. Please check it out online. Go to our website. We'd love to see everybody there. And we also have a cardiac safety symposium coming up. If you're interested in cardiac safety, this would be a great thing to check out. Again, thanks everybody for joining. Everyone have a wonderful rest of your day.